All right, so you want to explain properly Faraday's law and Lenz's law, and then use them to explain the generator, right? Right. So let's take a quick little definition on what is Faraday's law and Lenz's law, and then I'll show you how it works, right? So write this down. Write this down for Faraday's law. Right? If you remember last week, right? The writers here. If you remember last week, right? When we were doing the little simulation and I had a magnet, the faster I took the magnet and I moved the magnet in and out of the coils, the larger was the EMF. Remember that? The brighter the bulb of light. Remember that? So I took the magnet and I moved the magnet in and out. And the faster I did it, the larger was the brighter was the coil. Okay? So that's basically Faraday's law. Faraday said that these field lines here, you see these field lines, these magnetic field lines, the faster those field lines are cut by the conductor, the bigger is the current or the voltage value. Really is the EMF value, right? EMF is voltage. Are you okay with that? That's basically what Faraday said, right? So write this down. Faraday's law states that the rate at which Faraday's law states that the rate at which the magnetic field lines cut the conductor, the rate at which the magnetic field lines cut the conductor is proportional to the EMF, put in brackets, voltage produced. It's proportional to the EMF put in brackets, voltage produced. Right, just draw this fast. You all have it already? Draw that fast. And I'll give you something to write underneath it. Right, underneath this, write this, please. The faster the magnet moves in and out of the solenoid, The faster the magnet moves in and out of the solenoid, the faster the magnet moves in and out of the solenoid, the greater is the deflection on the galvanometer. The greater is the deflection on the galvanometer. The greater is a deflection. So you see there's something down here. This is your galvanometer, right? Yeah, look at it. Galvanometer, right? So the greater, the faster you move the magnet in and out, the greater the deflection of the galvanometer. So the faster you move the magnet, you would recognize that the galvanometer will go all the way down here and here. That's okay? So the faster you move it, the bigger is the EMF. And the main reason for that, huh? No. I was making too much of noise last week. I ain't doing that again. Right? The reason for that is that the faster you move it, right? Basically, it's the greater amount of mechanical energy that you're using. And the more mechanical energy that you supply, is the more electrical energy available during the conversion. That's okay? That's one of the reasons, right? Okay, nice. Right. Now we need to figure out the direction. We need to figure out the direction of the current being induced here. That's where Lenz's law comes in. All right, so write Lenz's law now. Lenz's law states that the direction, Lenz's law states that the direction of the induced EMF, Lenz's law states that the direction of the induced EMF always opposes the motion, always opposes the motion put in brackets slash direction, close brackets, of the incoming magnetic field, incoming magnetic field. Okay, so I want to explain this, right? This one a little bit harder, right? So watch this here. The first one easy, you move it faster, you get bigger deflection, right? Now we're looking at direction. So watch this here. Let's say the magnet moving in. So I'm going inwards first. Right? Right. Here's what has to happen, right? It has to oppose motion. So you have to figure out now what magnetic field or what pole has to happen here to oppose the motion of a node coming in. What pole on the end there will oppose a node coming in? A node. A node will oppose a node, right? So good. A node has to be produced here to oppose the motion. Right? Now let's see if we can figure out the direction of the current. You all remember Fleming's right-hand rule? Sorry, right-hand grip rule? Right. So your fingers point in the direction of the current and your thumb points towards the magnetic node. Right? So you're using your right hand, right? And your thumb pointing towards where is north. And your fingers will point in the direction of the current. So the current coming down the coils. You're seeing that? The current coming down the coils like this. And notice on the right side here. That's okay? So now you have to follow the coils. So watch it here. I'm focusing on the end. So it's coming down here, it's coming up here, it's coming down here. That's okay? So the current going to the right, and then it coming back up here. You're seeing that? And the galvanometer will follow the direction of the current. So the galvanometer will point in this direction to the right here. That's okay? So when the magnet moving in, the galvanometer will move to the right. Online, all okay with that? When the galvanometer moving in, it will move to the right. Okay? And now, if the galvanometer is moving out, what pole has to happen when they're moving out to oppose the motion? The magnet moving out, but you want to put it inwards, right? So therefore, here will be a south pole. A south will attract the magnet back inwards. So if here is south, then here is north, and current will go in the opposite direction. Are you okay with that? Yeah, draw that diagram, please. Color code it too. So you will know, right? Color code it. Hello? Yeah, well, you could cost on the you could be cost on the but yeah, on the description in the bottom.
Because I like I'll just do one. Yeah, that's true. I'm saying. Yeah, that's not what I'm saying, right?
So that is your lenses there, right? Sorry, I don't know what I said. I meant that is your magnet, right? I went to get the past paper for you, and I forgot. And we had a past paper booklet, yeah? Physics? Yeah. All right, so let's do a small application of this. Janet, hello? All right, let's take a look at 2017. If you have a soft copy, you can go ahead and use it, right? Let's take a look at 2017. It's June 2017. I just think no rotate in mind. Right, start this first part here for me. Right, so let's take a look at this here, please. Try this first. See if you can figure out what direction the galvanometer will move in, what direction. This is June 2017. Number one. Right, same thing that we just did, the magnet just on the opposite side. All right, try it fast. So back in the diagram, right?
So I wasn't on so the one on this way was. I don't know. Yeah, really quick. I want to say, I don't want to see. So. I don't know. Especially. Like a week, no, week in advance.
Next one. Using the rule, using the right hand rule. Your thumb will point towards the north and your fingers are what point in current direction. All right, so watch this here. You got this one? So let's see what we have here, right? So we have a north pole here. That's a north pole, right? So the magnet is pushed into the coil. So what do we have on this side here? A north, right? Good. So you're using your right hand grip rule, your thumb pointing towards the north and your fingers will point in the direction current. So based on what we see in here, the current coming up the coil. Okay. Thumb points towards the north and your fingers, right? So your thumb always pointing towards the north, right? So your thumb should be pointing here and your fingers will curl upwards, right? And whichever side here, your fingers pointing upwards here. So you go into the wires and your wires will point up. No, what you curl. Look at the curl. You have to always do it relative to the paper in front of you, right? Because we figure out the left hand side is north. So your thumb pointing towards north and your fingers curling and going upwards. Right? So they're moving like this and going up, right? So it's going up, it's coming down here, going up here, going here, going here. So the galvanometer will point in what direction? Towards the right, right? The galvanometer follows the current. Sorry? The galvanometer will follow the current. So the current going to the right, the galvanometer will go to the right. Right, so what your fingers are like the coils, eh? Watch this. Your fingers are like the coils. So it's going in at the top and coming out at the bottom. You'll see now? In at the top, coming out at the bottom. So your fingers kind of follow in the coil direction, right? Or your coil following the finger direction. Okay, nice. So that's the Lenz's law and your Faraday. What the next part? Explain why an induced current is produced. Why? What will be your explanation for that? What's the law that explains the induced current? Faraday's law, right? So what you will say is that a current is produced, an induced current is produced because by Faraday's law, right, magnetic field lines are cut in the conductor. right? Right. So yeah, as I was saying, by Faraday's law, the magnetic field from the magnet cutting the conductor, which produces an EMF, which will in turn produce a current. Okay. Good job, Shabani. That's okay. So you must state by Faraday's law, right? Because Faraday basically said that once the magnetic field cutting a conductor, an EMF is produced. Once an EMF produced, then a current will be produced as well. And the reason they would use the word induce is that when you stop doing it, it won't. Right? So the movement of the magnet inducing a current. Right? Why is it necessary to have a sensitive galvanometer? Sensitive, that's a word. That's a key word there. Right? Because these induced currents are small, want something that's sensitive enough to pick up that current that's being produced. All right, so make a note of that. Because the induced current is not large, the galvanometer has to be sensitive to pick up these small changes. Two parts again. Take a look at part 4 and 5. Try part 4 and 5. You have to redraw a diagram, right? Right, so to finish your online, tell me, right? I'll correct it. Okay, and you're doing it? You're doing it? Hurry up. Yes. Hello? Nice morning. Ready? Right, remember you have to do part 5 as well. Huh? Ready? All right, so let's go. We shall have it, so let's go. Right, first thing first, the magnet moving out, right? Yeah? So what pole do you have there? Next step. But what pole do you have here? The magnet coming out. What pole do you have there? Here's north. So what pole do you have here? South. But yeah, I tell me south, I can't read your mind. So here is south and here is north. So what direction is current moving in? Down the coil, up the coil. Show me on the rule. Show me using the right hand rule. Right? So basically your north is here and the current coming down. So it coming up and coming down, right? So the current going down the coils like this. Nice. So it coming up here and it coming down here. You're seeing that? So it going down the coils, follow it out. So follow it out. You will see it behaving like that. Coming down here and going this way, going this way. So what direction the galvanometer will be in? Follow the current, right? It will follow the current. Oh, you're pointing at that. Okay. Right. What are the three adjustments that we can make to make the EMF larger as area? What else? Increase the no, we try not the current. That's what you're obtaining. Right? Move the bar magnet faster. Right? Move the bar magnet faster. One more thing. Stronger? Yeah. Yep, we could use a stronger magnet. Good job, Zane. Good job, Nisha. And Nisha will tell you, yeah. Zane is BA. Right, so those are your three changes, right? Nice. Let's take a look at how the generator works. Oh wait, I didn't take a picture of the generator. I'll pour back there for 1 minute. Let's, by the way, that's now. I'll compare that now. So you want to talk about the generator. All right. This here is the simple diagram for the generator looks. And let's look at a small simulation. So the generator will do exactly what it says. Generate current. All right, so the generator is going to generate current, right? So this is the simplified diagram of a generator. Anybody could tell me what are the two obvious things that are different in generator? Right, there are no split rings. There are slip rings. Yeah, split means they in half. What you have in front of you here are slip rings. Right, the motor has the half rings. Right, the motor has the split rings. Right, that's one major difference. There's the next thing that's different there. Yeah. What else different? Something else different. The no, the carbon brush there. Look at here. Something really important. Really important. Yeah. What is in there? What's different from the motor? Anybody seen it? Look at the motor and look at the generator. The generator doesn't have something that the motor has. Right, okay. So the generator has the galvanometer. Well, the important thing is that the generator does not have a supply. The generator does not have a supply. Okay? It doesn't have a supply. Because why? Exactly. The generator has to supply the current. Okay? Draw that diagram, label it up. Yeah. Draw it. Draw it again. Draw it, label it up, and then I want you to try to explain that. Hurry up, try to explain. I'm giving you 5 minutes. Try to explain the way the generator works, right? What do you think, Jaden? Hurry up, originally.
Not good to it. Yeah. Go on. Yes, I think you're much of it. Is it? Any chance? No. Raising your brain.
Right. We hear your explanation, Shabelle.
Yes.
What's your explanation for why how it works? Right? How do we get that current here? How do we get that induced current? Right? When the coil starts to spin, what will happen? So you have to apply a force, right? So when you apply a force in coils, what will happen? Right? And then what I will do? Yeah, but why? Why it is when it spins, you will get the EMF. Why? Because of the magnetic field. So the magnetic field staying right where it is, and by Faraday's law, because the coil cut in the field lines, what will happen? An EMF will be induced, right? So there are magnetic field lines between the north and the south, and as the coil moves, the coil will be cutting it, right? And the faster the coil cuts it, the bigger is the EMF being produced. Lenz is only to give direction, okay? The lens basically tells you that direction will always be opposite to the direction of motion. Right, but what's the rule that we're going to use to figure out current direction? No. What's the rule? The next rule that we use to get the actual current direction? Right-hand rule. Remember? If you have the force and you have the magnetic field, if you have the force and the magnetic field, you can work on current. Yeah, generator rule. So use the generator rule for me and see if you can figure out what direction current moving in from P to S or an R to Q. Use the right-hand rule and see if you can figure out what direction current moving in. So is it moving P to S or S to P? Hi, Prasad, what do you think? What direction current moving in? What's the force direction here? It's moving upwards here. That's the force, right? And it's moving downwards here. So it's turning, according to how you look at it, it's turning clockwise, right? So you have to use your right-hand rule to see if we can figure out what direction current moving in. Right? Hyposad said, okay, right. You have answer already. But now you see. So let's have to draw it, right? So the force going up, focusing on PS. The force going up on PS, the magnetic field going north. Remember, it's a right-hand ruler. Magnetic field going north to south, and my middle finger pointing from P to S. Check it and see. Right, check it and see. So your thumb pointing upwards, your index finger pointing from north to south, the magnetic field. Huh? Are you okay with that? So the force going upwards. You know again it? Right, so you're using Fleming's right-hand rule. So on the right-hand rule, the middle finger, the thumb is the force, right? You're applying the force. Your index finger is the magnetic field, and your thumb is what your middle finger is what we're trying to figure out. That's the induced current, right? Right. So thumb is the force. So the force going upwards, the magnetic field going north to south. So what direction current moving in? P to S or S to P? Look at the middle finger. Is it pointing P to S? Correct. Do the next side one time. Do RQ now. Do R to Q and tell me what you got. How it moving? Yeah, how it moving? It moving R to S. Sorry, R to Q. So the current moving like this. Are you okay with that? Right? If the period of rotation is 0.02, then frequency is what? Highest time frequency. Frequency is what? Area. Anybody remember what frequency? Frequency is what? We have period. We don't have V. Where I get V from? That's a waves. Frequency is 1 over 1 and period. So it's 1 over 0.2, which is how much? 1 over 0.2 is how much? 5. What over 0.02? 50 hertz, right? Right. Okay, good. Wait, I still didn't give you the explanation for the generator. So write these steps down. Write these steps down to explain the generator. Actually, wait, I want to pick on somebody. Nisha, how you would explain generator? Think of the first thing. Do it in steps. The first thing is what? A force applied to the coil, not to the magnet. Yeah, explain this. Right, yeah. The force is being applied to the coil. Right? And then what will happen? After you explain the force moving, after you apply the force, sorry. Second thing is what? Try and do it in point form, right? You remember that easier. What's the law you have to use? No, you use the right-hand rule last, right? The law you have to use to explain the EMF being produced. Faraday's law, right? You don't really have to use Lenz's law here, right? Right, because we're going to use Fleming's right-hand rule. So you're going to start number 1 with applying a force. Number 2, you're going to talk about Faraday's law when the coil cuts the field lines. Number 3, what are you going to do? Or what's the tilting? Right, you're going to use Fleming's right-hand rule to find current direction. All right. And then the last thing, it basically state that mechanical energy was converted into electrical energy. Okay, so just write down the point form. It's always easier to kind of remember that. First thing, the first thing you're going to say is the direction you're applying the force in. Direction of force, number one, direction of force applied to the coil. Notice their coil label, right? Recognize that? So when you're doing your thing, you have to label it. So you're going to say upward force on PS, downward force on RQ. Label your coil. What's that? Dotted line in the middle is just the axle. So number one, direction of the force. Number two, application of Faraday's law. Application of Faraday's law, that's number two. Application of Faraday's law, number two. Number three, use Fleming's left-hand rule. Use Fleming's right-hand rule. Left-hand rule is what again? Left-hand is the motor, right? Very good, you know. Right-hand rule is, right? Use the right-hand rule to find the direction of the induced current. That's 3, right? Use Fleming's right-hand rule to give you directional current. And 4, talk about the conversion of mechanical energy into electrical energy. That's a simple version, right? What I will do is I'll crop one for you and I will send you a word in, right? Yeah, conversion of mechanical to electrical energy. That's it. You can now start step 1, 2, 3, 4, right? No, now you can talk about that is the use of the slip ring. Right, but I will send you one that explain everything, right? It'll also give you a little more in-depth into the AC, but I feel like they stop testing you on that. Right? It will go a little more in-depth how the core rotation gives you the alternating current. Okay? All right, online. So I will send you explanation of what you could write up for this Faraday's for this generator, right? By Samira, I'll send you one to look at. Right, for the generator. Tomorrow, I mean next week we'll be doing the transformer. All right, that's the last thing in magnets. All right, online. So that's it. You all could log out.